In a previous screencast, we discussed how the stresses on a material depend upon the angle at which you're considering it. And in this case, we had a tensile test clamped in a machine, and we pulled it apart along the long axis with a force of F. And we considered hypothetical cuts into the material at 0, 30, 60, 75, 105, 120, 150, and all the way back to 180. And we noted the fact that if we cut it at 0 degrees or at 180 degrees, we're examining the exact same configuration of the material. If we draw a coordinate axis on the sample, we've got the x-axis running horizontally, the y-axis running vertically in the direction of the tensile load, and the z-axis comes straight out from the face of the sample. Then we'll take these axes and we'll rotate them counterclockwise with an angle theta, and the x-axis we'll call this the x-prime axis, rotated from the x-axis, and we'll call this the y-prime axis. And now the x-prime axis runs parallel to the cut, the y-prime axis acts normal to the cut, and the z-axis doesn't move. And the problems that we're looking at right now are known as plane stress problems. So if we're dealing with a two-dimensional problem, we rotate about the z-axis, but we don't rotate about any other axis. If you were to examine this in 3 dimensions, we would be looking at a differential element that would look like a cube. But for two-dimensional problems, our differential elements look like squares, and we can rotate these squares to any angle. Here I'm rotating it to 30 degrees. We could arbitrarily rotate it to 45. Or if we come up to 90 degrees, our x-prime axis now is coincident with the original y-axis. And we can continue down all the way to 180 degrees, in which the x-prime axis is now coincident with the x-axis, and the y-prime axis is coincident with the y-axis. Another thing we investigated was how the stresses acted on the differential elements as a function of the angle at which we rotated it. Here in red I'm showing the normal stress in the y-prime direction, and as we rotate it, the black arrows represent shear stresses, and the blue arrows represent normal stresses acting in the x-prime direction. So we looked at these. The size of the arrows represent the magnitudes, and what we found is that at 90 degrees our configuration was the same, except the red arrow is now a blue arrow, and as I continue rotating it eventually to 180 degrees, we return to the original configuration because the angle is offset by 180. I use those arrows I found the length of those arrows The length of the arrows I found using the stress transformation equations with sigma x prime in blue, sigma y prime in red, and the shear stress tau x prime y prime in black. And to solve the problem, I first had to have knowledge of sigma x, sigma y, and tau xy, and that's all I need to generate the transformed axes at the transformed stresses at any value of theta. And when we say we know the state of stress, it means that you know values for sigma x, sigma y, and tau xy at the outset at a value of theta equals 0. And to come up with these values, we have to know something about the problem. In this problem, we know that sigma x must equal 0 because there's no tensile or compressive force on the sample in either of these directions. There is also no shear stress in this configuration. There's no tendency for the sample to be shifted, for example, to the left above the differential element and to the right below it. However, there is a normal stress in the y direction. We just say that is equal to the force divided by the area. For this problem, let's assume that a force of 500 newtons is being pulled on the sample, and we've got a cross-sectional area. Let's say it's a centimeter wide, a half centimeter deep, gives us an area of a half square centimeter, and I run through the calculations being careful of units, and I find that the normal stress in the vertical direction is equal to 10 megapascal. So that means I know the state of stress in this configuration. Sigma y is equal to 10 megapascal, sigma x is equal to 0, and tau xy, the shear stress, is also equal to 0. Something worth noting about these equations is that if theta is equal to 0, cosine 2 theta is equal to 1. And sine 2 theta is equal to 0, and these terms will fall out of the equation. We find that sigma x prime is equal to sigma x, sigma y prime is equal to sigma y, and the shear stress tau x prime y prime is equal to tau xy, of course, if we haven't rotated the element. The same thing is true if sigma is equal to 180 degrees, simply because we've rotated it all the way around and the axes are in the same direction. And if we look at the differential elements, we do see that they indeed look identical at theta equals 0 and theta equal 180 degrees. Now if I set theta equal to 90 degrees, we find that the cosine of 2 theta, or cosine of 180 degrees, is equal to negative 1. And the sine of 180 degrees is equal to 0, so these terms drop out. So what we find is when theta is equal to 90 degrees, sigma x prime is equal to sigma y prime is equal to sigma x, and tau x prime is equal to negative tau xy. And indeed, this is the case when I look at sigma x prime that's equal to sigma y, the original stress in the vertical direction. So these arrows changed from red to blue. Let's graph these equations. If we know, when we graph it, let's say we know sigma x prime, we know sigma x is a value. So let's graph these equations as a function of theta. We know the state of stress in this problem when theta is equal to 0, sigma y is equal to a value of 10 megapascal, sigma x is equal to 0, and tau xy is also equal to 0. Note that to complete these graphs, all we need to know is the state of stress at theta is equal to 0. And everything else, the cosines and the sines of the period of these graphs don't depend at all on the initial state of stress. They just depend on the value of theta that you use. Let's also consider some other problem in which we know the shear stress tau xy is equal to 15 megapascal. Sigma y is equal to 3 megapascal, and sigma x is equal to negative 8 megapascal. Now these values we would have to know from the problem statement itself that for whatever reason the material is under compression in the horizontal direction, under tension, a little bit of tension in the vertical direction, and it's under shear stress. In these specific values, you'll need to use the equations from earlier in the class to come up with these values. Here's a graph for this state of stress. We've got the shear stress at theta equals 0 equal to 15. We've got sigma y is equal to 3, and sigma x is equal to negative 8 megapascal. And some things we observed mathematically is that at 90 degrees, sigma x prime is equal to sigma y. And sigma y prime is equal to sigma x. And the value of tau xy prime is equal to tau xy, in this case negative, is equal to negative tau xy, in this case negative 15. At 180 degrees, we found that tau xy, sigma y, and sigma x are equivalent. And finally, for this problem, if we're trying to find the state of stress at various angles at the dot in the tensile sample, it's helpful to look at how the differential element rotates as with values in the graph. So we start out at theta equals 0. We rotate it, theta, here's theta equal to 30 degrees. Again, we know the initial state of stress is sigma y prime is, or sigma y is equal to 10 megapascal. Sigma x and tau, xy, are both equal to 0. And as I continue rotating it through, it's 30 degrees. Here's a value, here's a situation in which the shear stress is maximized. And it turns out for this configuration of this state of stress, the shear stress is maximized at 45 degrees. So a ductile material would tend to fail along this angle. Ductile materials fail where the shear stress is the largest. And if I continue rotating now, we come up to 90 degrees, and here the normal stress, sigma x prime, was equal to sigma y prime originally. Those vertical arrows are now blue. And if I keep rotating all the way around to 180 degrees, we'll come up with the original configuration. And brittle materials that tend to fail under excessive normal stresses would fail at value equivalently a value of 0, 90 degrees, or 180 degrees. In other words, they would fracture. This particular sample would fracture horizontally.